A very warm good afternoon, ladies and gentlemen. I, Engineer Manju Guru and Engineer Paribesh Priyar, your MC for today's program, would like to welcome all of you for a half-day seminar on slope stability works on the Nepal mountains, organized by Nepal Geotechnical Society, Kathmandu, Associate Partner, Geotechnical Engineering Program, IUE Full Campus, and Nepal Landslide Society. Sponsor, Geo Switzerland. Co-sponsor, East Management and Engineering Service Private Limited, Laripur. Tactical Solution Private Limited, Laripur. And Clay Engineering, Kathmandu. Our web internet and payment partners, Khati. Now to chair the program, may I invite Dr. Indra Prasad Acharya, Vice President of Nepal Geotechnical Society, on the dais. I would like to invite the Chief Guest, Engineer Keshav Kumar Sharma, Director General, Department of Road. Sir, please, on the dais. Mr. Shiva Prasad Nepal, Executive Member, Nepal Geotechnical Society. On the dais, please. Mr. Danish Gross, Representative and Keynote Speaker from Geo Switzerland. And Engineer Tuklal Adhikari, Past President, NGS, and President of SCAF, Society of Consulting Architectural and Engineering Firms. I would now like to welcome our special guests who have graced this program with your presence and request them to please rise at this respective seat for acknowledgement as I spell out the names. Engineer Buti Raj Joshi, Representative, Dean Faculty of Science and Technology, Pokhara University, former VC, Pokhara University. Or Engineer Kulman Gisik, Managing Director, Nepal Electricity Authority. Mr. Achyutanand Bhandari, President, Nepal Landslide Society. Dr. Jagat Kumar Shrestha, President, Structural Engineering Association, Nepal. Engineer Madhukar Prasad Raj Bhandari, Director General, Department of Water Resource and Irrigation. Engineer Mani Ram Gelal, Director General, Department of Urban Development and Building Construction. Engineer Ramchandra Shrestha, Director General, Department of Local Infrastructure. Few of our distinguished guests have already joined us, and we will be joining in the session shortly. Moving forward, I would also like to welcome our special guest from Kathmandu Tarai Fast Track Project, representative from Vikas Nirman Nishanale, Nepal Army, Chief Behnam Dalili, Local Road and Bridge Program, DSP Milanman Maske, Service and Support Directorate, Armed Police Force, Dr. Ranjan Kumar Dahal, President, Society of Engineering Geologists, Nepal, and Dr. Ram Prasad Ghimire, President, Nepal Geological Society. I would like to take a few moments to introduce our organizing committee, without whose dedication and hard work this seminar would not have been possible. The chairperson of organizing committee, Dr. Vishwaranjan Shahi, Past General Secretary, NGS, Professor Dr. Netra Prakash Bhandari, President, Nepal Geotechnical Society, and the whole executive team, Professor Dr. Atal Bahadur Singh, Past President, NGS, IE Full Campus, Engineer Tuklal Adhikari, Past President, NGS, Engineer Indu Sharma Dhakal, Past General Secretary, Engineer Uttam Lal Pradhan, Past Executive Member, NGS, Past Joint Secretary, DUR, Engineer Amod Adhikari, Senior Geotechnical Engineer, Engineer Naresh Manshakia, Geotechnical Engineer, STE, DUR, Engineer Anantaraj Ghimire, Geotechnical Engineer, Dean Faculty of Engineering, Midwestern University, Engineer Buti Raj Joshi, Geotechnical Engineer, Dean Faculty of Engineering, Pokhara University, Engineer Sujan Mata, Geotechnical Engineer, Principal, Kupa Engineering College, Dr. Dhundi Raj Pathak, Geotechnical Environment Engineer, Engineer Suman Wagre, Geotechnical Environment Engineer. Engineer Mavin Dahal, President, NGS Student Committee. Engineer Govind Nirola, Executive Member, NGS Member Secretary. Now moving towards the inaugural session, I request the chairperson, Dr. Indra Prasad Acharya, accompanied by the chief guest, Engineer Keshav Kumar Sharma, DG, DOR, and other distinguished dignitaries on the stage for the traditional lighting of oil lamp. Without further delay, ladies and gentlemen, to officially welcome all of you, I request the chairperson of today's seminar, Dr. Indra Prasad Acharya, for the opening remarks.
Thank you, Manju. Chief guest of this program, Director General in Department of Roads, DDG in Department of Roads, and representative from different organizations. Similarly, President of ISCAF and different participants from different organizations. From GeoBrook Export. Similarly, sponsor of this program, co-sponsors IMES, Engineering, and Department of Geotechnical Engineering Program from Institute of Engineering. I would like to welcome all the participants. With a number of recent plans of building new infrastructure such as fast-track roads, express highways, railways, high dam reservoirs, and so on in the country, the scope of slope protection work is expected to grow exponentially. Local consulting engineers and construction companies are still new in this field, but within the next 5 to 10 years, it will be inevitable that we must running in many different technologies in slope protection and management works. So this is the right time Nepal Geotechnical Society should take the lead to discuss various aspects of slope and strategic issues in the Nepal Himalaya and must facilitate international companies to introduce their product and technologies in Nepal. This seminar will address these issues and bring all stakeholders of slope protection work in Nepal together to discuss the opportunity and challenges in protecting Nepal's slope. I would like to welcome all of you. Thank you.
Thank you, sir, for that very sincere and warm address. Nepal, a beautiful landlocked country in South Asia, is characterized by more than 80% of total area covered by hills or mountains. So it becomes inevitable for the infrastructure development, be it roads, bridges, hydropowers, buildings, etc., to be constructed without paying attention to the slopes encountered therein. Except for a few recent roads that can be countable in fingers, we vastly practice the traditional measures like cabin retaining walls, stone masonry walls, and vegetation cover for all slope protection works. The reason for this may be attributed to limited resources and lack of new and affordable technologies applicable in a country like Nepal. Thus, there is an urgent need of modern systems and technologies for slope stabilization in this country, Nepal. On that note, ladies and gentlemen, though the president of NGS, Professor Dr. Netra Prakash Bhandari, could not make up for today's program, but he has conveyed his good wishes and success of this seminar and has sent a small speech which I am going to request Engineer Mandeep Subedi, General Secretary, Nepal Geotechnical Society, to read it out.
Good evening, everybody. On behalf of our President, Professor Netra Bhandari, I am reading his speech. Ladies and gentlemen, first and foremost, through this message, I extend my sincere apologies for certain limitation at my side and have led to my absence in this program today. Being away from Nepal and going through an extremely busy time, mainly because of semester thesis defense and so on, I have not been able to attend this seminar this time. We attempted to plan it in the end of February, but due to a few difficulties, we had to hold it today on 18th February. So, yes, to extend my personal as well as society's appreciation to all participants and speakers of the seminar, I have prepared to go with the text message. Our country, of more than 80% of mountains, we cannot avoid slopes while developing our infrastructure of any scale and any type. We have suffered a tremendous loss in the past because of roadside slope failure and slope failure-led natural disasters. Despite being one of the most important field of soil mechanics and geotechnical engineering, slope instability issue is still somewhere in an unattended corner of Nepal. Mainly because of heavily low-cost hill road design practices, heavily biased use of bioengineering techniques in slope stabilization, a little willingness of authorities to go for heavy structures to ensure road safety, land safety, and appropriate land use planning. We have no better option than to go for more and more engineering structures in Nepal too. So, I am confident we have rightly decided to hold this seminar on this important topic today and have invited experts in the field to shed light on the slope stability analysis and stabilization technique. Nepal Geotechnical Society heartily welcomes you all the speakers in this seminar, and representing the whole society family, I extend my heartfelt appreciations to you all for accepting our request to make appreciations. Thanks very much. The audience is always important, and I have always felt that the audience strength makes us evaluate how successfully we have organized the program. In your presence and overwhelming interest of yours in all your recent activities have recently encouraged us to do more and more in the days ahead. We thank you all from the bottom of mind as well as our hearts. Thank you so much. I hope this seminar will be very successful in terms of learning recent trends in slope establishment techniques. Interaction makes a program more successful. So I hope all our young members and participants will interact with the speakers, senior members, and experts. If not during the presentation, during the interactive dinner too. Thank you, and I wish you all the best. Netha Prakash Bhandari, President, Nepal Geological Society, AIML University, Japan, 18 February 2020, from Matsuyama, Japan. Thank you.
Thank you very much, sir, and Professor Dr. Netha Prakash Bhandari for that kind gesture. And we hope that we are going to take as much as we can from this very informative seminar. Our distinguished guest, Engineer Keshav Kumar Sharma, Director General, Department of Road, has made to the inaugural session, and due to his responsibilities and busy schedule, he has to leave us at this point of the program. May I ask him to convey his remarks for today's seminar?
I am very much pleased and privileged to be here in this precious seminar organized by the Geotechnical Society. First and foremost, I would like to thank the organizers for inviting me in this very important seminar. But due to some responsibilities, I have to leave the seminar before the main papers will be presented. I am very much sorry for that. Regarding the geotechnical field, Department of Roads, we are very much awaiting to join hand with geotechnical societies in our slope stabilization works. Yes, we have expanded our scope for many east-west and north-south highways, widening and developing new highways. So there is no way to encounter with the very fragile scopes. I am very much pleased that I could see many of my colleagues from DOR are the members of Geotechnical Society, but still this number is not sufficient, as I think in comparison with the challenges we have in the field of slope stabilization. So we need, yes, we have some in-house, DOR in-house experts, but still we need many experts from the Geotechnical Society. There could be domestic experts and also some foreign experts as well. So that I think this is a very good opportunity for me to interact with Geotechnical Society so that I could not be absent in this program and I could manage at least to attend in this opening session. I think still Geotechnical Society is working in very professional way, but not in entrepreneurial way, I think, because there are many challenges of slope stabilization, but I am waiting for the hands from Geotechnical Society to work with many stakeholders like DORs. We can make MOUs, we can work together even in the early stage for small projects, and we can expand our field or our portfolio for bigger projects as well with Geotechnical Society. Just now I think we have some discussion with the tunnel, Siddha Baba tunnel and Lama Baba tunnel with Geotechnical Society. I had already interacted with my colleagues and requested them to make discussion and interaction with Geotechnical Society so that we can get input from Geotechnical Society. So I think there is very much potential of geotechnical engineers in this country. As already we have talked that Nepal is mostly 80% hill and mountainous country, so this is our prime challenge to stabilize the slopes in various construction projects. One of them is Department of Roads, and we are, as a DC of UR, I wish to say that Department of Roads is keen to join hands with Geotechnical Society and also keen to have your expertise in our projects. I wish very success of this seminar, and I am sorry to not be the part of the successive sessions. Thank you very much, and I am thankful again for the invitation. Thank you.
Thank you, Keshav Kumar Sharma, DG, Department of Roads. Well, ladies and gentlemen, we are again back on the main part of this seminar with our first keynote speaker, Dr. Shankar Thakal. I request him to be on the podium for his presentation.
I have been using this platform to share my knowledge and skills when one of my co-supervisors is the president, and I can see most of the participants, either my teachers or colleagues or friends. Well, I have tried to give the title of my presentation to be Rockfall Protection Engineering, and I will be highlighting some of the outcomes of our detailed project report, DPR, of Siddha Baba rockfall protection project. And that project was actually undertaken in 2016 when Uttam Pradhan, Senior Superintendent Engineer of Western Regional Directorate of Department of Roads, was the leader. And I was the team leader on behalf of the consultants. Well, I'm trying to share some of the issues of rockfall protection under the heading of rockfall engineering, rockfall protection engineering, Siddha Baba rockfall protection DPR, its evolution, and in the end, I'm trying to highlight some of the structural engineering aspects of rockfall protection engineering, and there is an interesting proposal for how we can introduce innovation in rockfall protection engineering in the context of Nepal that is both resilient and sustainable. Sometimes we try to highlight enough on safety and resilience, but we miss the component of sustainability or environmental sustainability. And glad that one of the experts of environmental science and engineering, Mr. Wagle, is with us as well, and he was a part of Siddha Baba DPR. Well, actually, when I was pursuing my PhD in 2012 in Japan, to be very honest, I didn't know anything about rockfall. I wanted to pursue a research on Rockfield Dam. That was the topic of my master's degree thesis. However, I happened to be interested in rockfall and rockfall protection and structural engineering and pursued that. So some of you might not be aware of this term rockfall. Actually, rockfall is nothing but falling down of fragmented rocks from the uphill. And in the downhill, there could be road, railways, or even buildings, settlement. So those rocks can hit those infrastructures and cause fatalities or damage to the property. All right, so we mostly know about landslides, and there have been a lot of research on landslides actually, and some of our own native researchers, including Professor Dahal, Netra Prakash Bhandari, have researched a lot on that area, but I think rockfall is still a juvenile field for us to research. So what happens is, look into that picture, the fragmented rock, when it falls down, all right, if it is not protected on the hill, or if it is not protected from hitting the infrastructure, then you can, easily speculate the possible accident or disaster. So a rockfall is just the falling down of rock boulders or rock blocks from uphill to downhill. Okay, let me just introduce that. And in terms of Nepal Himalayas or Nepal mountains, it's very, very prominent. For example, after 2015 devastating earthquake, there have been a lot of rockfalls in Kodari Highway. All right, you can see the first two pictures are very disturbing pictures actually. Many vehicles and motorbike riders were actually killed in that event. And there is another popular site for rockfall hazard in Nepal, which is Siddha Baba. And the middle picture is from 2012, when I was the team leader of rockfall investigation. That's what we call it, rockfall and geological investigation. And the last one is the picture taken in 2016, when I was the team leader of rockfall protection DPR. So there has been an interesting evolution of rockfall protection research and rockfall protection practice in Nepal. Well, generally, as structural engineers, we think of our job to be design of reinforced concrete or steel buildings. And architects think similarly. They want to make the functional use of our buildings more comfortable. Okay, but we generally miss the scope of structural engineers and architects in making other various infrastructures, mega infrastructures, or national pride projects practicable as well, and rockfall protection is one of them. I'll show you later some of the pictures of rockfall protection structures where you can easily imagine the role of architects as well. That's very interesting if some of the members are architects. What is the science and engineering involved in rockfall protection? Actually, when we design project, we assign different roles: a geologist, engineering geologist, structural engineer, geotechnical engineer, environmental engineer, hydrologist, etc. But rockfall engineering and rockfall protection engineering is that specialization field which requires specialization as well as interdisciplinarity. Okay, you have to know about geology, you have to know about engineering geology, you have to know about geotechnical engineering and structural engineering as well. For example, look where the rockfall starts from. What would be the size of that rock block? That comes from various philosophies of joints and fractures in rock crop or rock hill. So you have to know some fundamentals of geology there. And when that rock block gets detached, it falls down and it can bounce on the ground. It can slide, it can have some energy dissipation there. That is where engineering mechanics comes, or engineering dynamics comes. Now you have to protect that falling block. That is the point where structural engineers have to play their role. And of course, these structures have foundations. There might be anchor, there might be other energy dissipation systems, etc. And there comes geotechnical engineer's role. And indeed, I again want to highlight that our infrastructure development should be sustainable as well as resilient. So we have to think about environment as well. So if we think about environment, science and environmental engineering in rockfall protection, there comes the role of environmental engineers as well. So what I'm trying to highlight here as the fundamental concept is rockfall engineering is an interdisciplinary field, and rockfall protection engineering is such a beautiful field of specialization which requires interdisciplinarity. Now let me little bit penetrate into the evolution of Siddhababa DPR. Actually, in 2012, when I was pursuing my PhD, BBC Nepali came to Ehime University and they took our interviews. And that was the point when I introduced the possibility of doing rockfall protection in Nepal and in Siddhababa site. And an engineer who was one of my friends of Phunchor campus, he happened to design an investigation project, and I was the team leader, and I was back in Japan. And I engaged my colleagues in Nepal, and it was done distantly. We prepared a report, it was in 2012, and we tried to find what are the reasons of rockfall, and what could be the possible intervention measures, what could be the possible protection measures. And back in 2016, under the leadership of Uttan Pradhan, we happened to design a DPR for rockfall protection in around 2 kilometer stretch of Siddhababa Road. And now we are in NGS special seminar, and I hope that the recommendations made in 2016 on rock sets in particular would be implemented ahead. And thanks to Geoberg for sponsoring this important event, and we are actually becoming a history of this infrastructure development transformation in Nepal. Yes, there have been some case studies done in rockfall protection flexible barriers by other entrepreneurs, enterprises, and other researchers, but rockset has not been introduced at all. But of course, when it comes to hydropower or or buildings, settlement in the hill, or dam or roads, railways, there have been a lot of talks about railways, and even to make the railways resilient, we have to go for rockfall protection structures, which could be flexible barriers, cable net, rock net, or rock sets. So this is actually a historic evolution of the research on Siddhababa rockfall protection. And in 2016, I don't want to go in detail of this because it has been already submitted to Department of Road, and you can actually refer to that report. We actually recommended 2 types of rock sets at different chainages. And those rock sets as concrete structure with cushion layer on top of it has been recommended. To give a brief snapshot, look at different stretches of the road of around 2 to 3 kilometer. We have proposed different structural protection, rock net, rock sets in particular, and in some of the regions we have recommended wire mesh as well. Look, so what rock fall protection structures are? Okay, it could be that you don't let the rocks falling from the hill by using anchor or by using some kind of wire mesh. That is called active protection. But sometimes it is not practicable or economically feasible to do that, and you let the rocks falling into the ground, okay, into your roads or railways or buildings. In that case, you have to intercept that falling rock. How you do that? You have two methods. One, put some structural system so that that system catches that rock, okay, by undergoing a large deformation. That is called rock net. I'll show you some pictures later. Or build some kind of umbrella structure and let that rock hit on top of that umbrella structure and get deflected to the downstream in the rivers, for example. Okay, so that is called rock set. So rock set is basically a gallery structure. In Switzerland, Europe, they basically call rockfall protection gallery, and in Japan, they call rock set. And America, as well as other parts of the world, have actually referred to these kind of solutions developed by Japan and Europe. So Japan and Europe are basically really fantastic places to do specialization on this field. All right, so that is rock net. See, when the rock hits the net, then the block is actually caught by the barrier. It undergoes a large deformation. Large deformation when there is force. What does that mean? Work done. Force times displacement. That work done is the energy dissipation. So that block carries some energy, mgh. For example, that block is falling from a height of h, and if it has got mass m, then its potential energy is mgh. That potential energy, when it falls down with some dissipation during bouncing, etc., it converts into kinetic energy, half mv square. And that is the energy which hits your structure. All right? So your net should be designed in such a way that that energy should be dissipated by your structural system by undergoing large deformation or by kind of other form of energy dissipation or by deflecting that energy by partial dissipation, which is rock set. All right, so this is rock set. Okay, rock set is kind of umbrella structure, and on top of that you will have generally practice sandbags or other kind of moored layer, and that moored layer or sandbag dissipates some fraction of energy, and the rest of the energy is deflected back to the downstream. And interestingly, actually one of my mentors from Switzerland, Dr. Axel Bolpin, was one of the leaders of this development, and Joburg as a company was the leader. They have actually developed this, what they call flexible rock set. You see this? Yeah, this is flexible rock set. So they have prepared the rock set of flexible cable net, which was one of the innovations. It might have its own limitations. Let me not focus on that for the time being. So what is the engineering involved in rockfall protection? How do we design rock nets? How do we design rock sets? It's very simple. Conservation of energy. Conservation of momentum. If you combine the principles of conservation of energy and conservation of momentum by modeling your system as single degree of freedom or double degree of freedom, depending upon whether there is cushion in between the rock block and the structure or not. For example, in the case of rock set, you might have to go into a double degree of freedom, and in the case of rock net, where there is actually not much energy dissipation when the block hits the net, you can model that as single degree of freedom system. And this very fundamental principles of mechanics and engineering do magic here. For example, let me show you an example of my own endeavor. So this was an innovative rock net developed in Japan. They call it LPR, long span pocket type rock net. Forget about that. Long span means generally it used to be smaller span. They made it longer. Okay, with longer span, the height has been increased, and it is pocket type because it actually intercepts the block. It's basically a flexible barrier, an improvised form of flexible barrier. And it is integrated with various energy dissipating system, friction damper. You have heard of that, yeah? Friction damper or fluid damper or other kinds of energy dissipating mechanisms. So it is integrated with friction dampers. Okay, so this system was subjected to full scale test and its deflection was conducted, measured, okay? And then I used a very, very sophisticated numerical program called LS-DYNA that can actually simulate the dynamic nonlinear behavior of the structure. And it was not easy to model that actually, because there were dissipators, there was a cable lay, there were cables, geometric nonlinearity, material nonlinearity, many complicated philosophies were involved. Anyway, through the use of LS-DYNA, we could exactly simulate the full-scale test behavior of this cable net. Once that is done, your numerical model is validated. Now you can use that numerical model for any parametric study in such a way that you have to develop some formula. You have to develop some chart, like the DZ of the Department of Roads said, there should be some entrepreneurial dimension of what we do. If we can't really relate what we do into real practice, then it will remain as a research. So I try to simplify this whole behavior into a simple equation that can be stipulated in our National Building Code. All right, and I propose some framework that can be directly stipulated in the National Building Code for roads, or some guideline of the Department of Road, like the government of Japan has put it in the road design guideline, or Europe has its own standard called ETAG 027, and ETAG 027 is one of the must cited and must referred guideline throughout the world. So we are glad that Joburg is there and their products are actually tested and validated to meet the requirements of ETAG 027 global code, although it was developed in Europe. All right, so what I did is I interpreted the whole behavior of the net through that simple formula, beautiful formula, very elegant. And with the use of that formula, now you can actually evaluate the performance of such nets. If you know the mass of the net, if you know the mass of the boulder, okay, and if you know some kind of structural behavior, okay, cable net, wire mesh, their properties, their elastic properties, okay. And what I have proposed is, in most of the guidelines, there is the design requirement for given energy. But look, you might have larger block, okay, falling from smaller height, or you might have a smaller block falling from the larger height, or you might have multiple fragmented rocks hitting on the structure having the same energy as a single block. Okay, that was not actually characterized in the existing codes, and I have been able to propose some kind of new guideline where not only mass of the block and height of the block, but the characteristics of the blocks and the different loading scenario, like impact points, those were incorporated as well. That was the one discovery that we did. Why I'm trying to tell this story, I'll relate very quickly. And also, we can actually improve the energy dissipation of those systems. All right, so we developed a new kind of friction brake energy dissipators by changing its constitutive model, by changing its stress deformation curves. And we call that Dhakal LBR brake model. It has been published in one of the journals of 2012. And what that model does is that enhances the energy dissipation efficiency of your system. And at the same time, I showed you a figure, right, before. Look, this net, if it escapes from the whole system, the net together with the rock block is going to hit your vehicle. So you have to make sure that the block doesn't come along the road. Okay, so in order to achieve that, I proposed a new solution of this. Sorry. Okay, in the end, you can see stopper, and also I changed the frictional properties of the U-bolt of the brake device. Anyway, and that gave the energy dissipation performance as good as one of the popular models developed by Kajani in Europe. All right, Now let me talk about some new knowledge. Actually, I wanted to describe a lot about rocknets and rocksets, but Dennis from Joburg was going to present here, and I assumed that it is not as appropriate for me to explain those products than himself, because he has got many hands-on experience. But I have incorporated a new chapter, and the new chapter, although the Department of Roads (DZ) has already left, there are other decision makers as well, and I really want to appeal to make this discovery the native discovery of Nepal, and let's implement this in Nepal. My proposal is, look, we proposed this in 2016 DPR as well. That is the rock set. Okay, rock set is basically a high strength concrete structure. Why do we have to go for rock set when there is very steep hill? Okay, the flexible barriers may not be able to stop those falling blocks. Because when you do rockfall analysis, it has got bound side. Look, if the bound side is say 12 meter and your rockfall barrier is just 5 meters, what will happen? Your rock barrier might be very strong, but it can't catch that falling block. Okay, so when there is very steep hill, when the block comes directly on the road, then you have to deliberately go for other solution. It could be rock set, or it could be reinforced earthen embankment as well if you have larger width of the road. But unfortunately, Engineer Pradhan knows how much we struggle to extend the width of the carriageway width of the road. We had to even add some supporting structure at the end of the road. So the width was really, really critical. And we also took suggestion from tunnel engineer about the excavation, chances of excavating the hill, but that was not really recommended, although we definitely advise some little thickness of the excavation. Now, if there is no width of the road, then you can't go for reinforced earthen embankment. You have to go for rock set. Now, I told you our infrastructure should be resilient as well as sustainable. That's what we call RESPRO, resilience and sustainability-based prosperity. We call prosperous Nepal happy Nepali, and prosperous Nepal happy Nepali comes from resilience as well as sustainable development. All right, so how we can make our rock set sustainable? You have been seeing a lot of tires, discarded tires, okay? And they have fantastic energy dissipation system. One of my colleagues in Australia, Dr. Hingo Sang, has been doing a lot of research on this, and I'm trying to commercialize those innovations by taking his consent. He has actually handed over the patent to me as well. So what we can do is, those tires, discarded tires, if used as cushion together with sand or soil to make it stable, then its energy dissipation phenomenon is many times better than sand. How? Look, the energy dissipation in your structural model or geotechnical models would be represented by zeta, if you know, okay? Zeta, damping coefficient. And that damping coefficient comes from actually this hysteretic energy dissipation behavior. This hysteretic energy dissipation behavior of rubber soil mix discarded tire is just fantastic. And most importantly, okay, there are other energy dissipation cushion layer as well, but RSM is the only solution which can dissipate the energy both in horizontal direction and vertical direction. And you don't know, your rock might hit on the rock set from any direction, that it might be inclined. So you have to have energy dissipation in both horizontal and vertical. How? Like this. Okay, that RSM, rubber soil mix, or the discarded tire, okay, dissipates energy both in rotation and translation in horizontal and vertical. I don't want to go into the dynamics of this, but look, when it was tested on a reinforced concrete building, without RSM, you can see the displacement, inter-story drift, which indicates whether the building would be damaged or not, is like that. But if you incorporate rubber soil mix at the base of the foundation of either vernacular building, okay, stone masonry or reinforced concrete building, then around 30-40% of your seismic shock would be absorbed by rubber soil mix. Now, if your vernacular building is weak, doesn't matter. Even if there is 8.2 earthquake coming in the western side of Nepal, maybe larger than the Gorkha earthquake, still 30% of the seismic action would be dissipated, and you just have to design for 70%. Marvelous. And actually, this was proposed in 2016 when I came to Nepal from Australia to support in post-earthquake reconstruction. Okay, as a part of my National Reconstruction Movement campaign, I tried to serve as an engineer in different rural districts: Kabre-Palanchok, Sindhupalchok, Gorkha, Sinduli, many different places. All right, so this was our proposal, and it was integrated with interlocking brick, and I was the team leader of getting it approved from the government of Nepal. You can see in Reconstruction Design Catalog Volume 2, there is my name acknowledged as the team leader. Interlocking brick was approved, but rubber soil mix is still, not too convincing. And now I have moved to Nepal permanently, and again trying to carry on that campaign, and hopefully, based on my conversation with CLPAIU friends of the government of Nepal, they are very positive to approve rubber soil mix. And someday we might be seeing a revolution of rubber soil mix RSM use in roads, in buildings, in other kind of heritage, site projects, etc. All right, and this is the self-funded project. Actually, I love, conducting research and supervising research. In 2013 as well, I supervised one of my researchers using my own fund, and we published a lot of journal articles, conference papers as well, and he has just recently finished his PhD and doing so well. So similarly, now I have another researcher, a graduate of Pulchar campus, and I have been funding myself, and he has been doing this research, and we have just completed the write-up and sending for the publication. I hope I don't have to do more when it comes to road. There are so many leaders of road departments and other departments of road. So I really appeal you, sir and madam, to facilitate for the funding of rubber soil mix use in road projects so that we can have our own native solution. Okay, so what is that native solution? All right, this is the research outcome of our use of RSM in reinforced concrete building. This is the inspiration for RSM use in road as well. And we have found that the vulnerability of the building is reduced by 32% if you use RSM in 80-story building. That means the seismic shock of the building is reduced, dissipated by 32%. Isn't that amazing? You can just imagine the cost saved. Okay, you have lesser size of columns, and when you have less dead load, the footing would be slim as well. See the consequence of using RSM in buildings. Now I have been proposing the use of this rubber soil mix or scrap tire in rock shed as well. What you do here is, okay, we have idea, we'll be modeling it using 2 degrees of freedom system, and my mentor at the University of Melbourne has developed a program to simulate that behavior of 2 degrees of freedom system. And with the use of that, by characterizing the cushion made of rubber soil, we can actually know how much energy is dissipated on that cushion layer. Once you know the energy dissipated on that cushion layer, for the remaining energy, you can actually design your concrete rock shed. And you can actually reduce the size of rock shed. That means you would have more carriageway width. You can actually save the cost with the same size. So such a beautiful solution that I really wanted to propose. And if you fund for this research project, otherwise I'll fund from my pocket anyway, doesn't matter. We should be able to design rock shed with rubber soil mix as the cushion layer. It would be our native solution of Nepal. Actually, if we could capitalize on that RSM used in building, in post-earthquake reconstruction, we would be the first nation in the world to use RSM in post-earthquake, integrated settlement planning and construction. But unfortunately, we lost that opportunity. Turmashintali has made some, settlement that is not, totally engineered or not totally innovative. We could be the Mahabirpur and Turmashintali of RSM in Nepal, and the whole world would come to see our resilient and sustainable post-earthquake reconstruction villages in Nepal that would have promoted our earthquake engineering tourism as well. But look, this is how life goes, have to struggle. Anyway, so let's work with NGS to use rubber soil mix in rock shed and use the hands-on skill of geowork-like companies and also our own native innovation and go ahead with it. This is what I really wanted to appeal, and thank you for kindly listening to me. Thank you very much.
Siddha Baba site along Siddharth Highway. More than 70 deaths in 3-kilometer stretch for the past years. Thank you, sir, and the whole team for the great effort you have put on to make the road safer. Now I would like to invite our next keynote speaker, Engineer Rohit Bahadur Bisural, Senior Divisional Engineer, Department of Road, for his presentation on slope protection works on DOR projects, a case study of Naranghat Muglin Road. Sir, please, on the podium.
Namaste everybody. I am Rohit Kumar Bisural. I was project in charge of the Naranghat Muglin Road project at that time, and now I have recently transferred to Coastal Road project as a project director. So I would like to put our experiences, what we have done and how we experienced from the slope stabilization works in Naranghat Muglin Road project on past few years. This Naranghat Muglin Road project, as all of us know, that the entire road alignment passes through the Mahabharat Himalaya mountains, and out of 33 kilometers of Naranghat Muglin Road project, whole road stretch was upgraded to Asian Highway standard in 3 ICB contract packages between the 2015 and 2018. The road was widened from 7 meter. Earlier the road was 7 meter wide, and it was widened to 10 meter in the hilly parts, and in the plain and rolling terrain it was widened to 11 meter. Large number of landslides happened there with road closures up to 47 hours at a time. So while the project was road construction upgrading was going on, the road was closed for 47 hours, even up to 47 hours at a time. And DOR and Donor World Bank realized that countries should pay special attention and provide slope stability measures in order to prevent people's life and preserve valuable assets. So here is a rough economic loss analysis due to road closure at Naranghat Muglin Road on 2018. We can see the vehicle types in the first column: truck, bus and light vehicles. Number of vehicles was counted at the Naranghat Muglin Road itself, and number of passengers, this tentative number of passengers on each type of vehicle. Hourly wage of one passenger, you can see here the rate of passenger, and average loss from one vehicle in 18 hours of traffic jam. So the total loss, economic loss in Nepali rupees is due to truck, haltage of truck say, and due to bus and due to light vehicles, all it comes out to be 21 crore 11 lakhs 13,000 for 18 hours of a traffic jam. So 50% of this goes to the Indian economy. The loss to the Nepal and goes to the India. And so economic loss per hour is rupees 1 crore 17 lakh 28,000 per hour. So I would like to show you some successful examples of slope stabilization works applied in several locations with extensive bioengineering measures at specific 39 places, with specialized works of rock netting at 8 places of 24 kilometer hilly section of Naranghat Muglin Road. This is geological map along Muglin Jugedi Road section of Naranghat Muglin Road, because Jugedi to Muglin comes under the Mahabharat range. This is one of the road construction practice in Nepal, showing the comparative study for rural road and Muglin Road. This is maybe not in Muglin Road, but for all the national highways in hilly parts of Nepal. Here the condition one is existing natural slope is like this, and the shear zone is very deep here in the rural road, and in Muglin Road the shear zone is cut by the road section itself. The condition, second condition here is in rural road, slip surface of huge old landslide is not active here. The slip surface is below the road section, and in Muglin Road or most of the national highways with wider road section, the bedrock is cut by the road. Here I have shown one of the photograph of slope failure in the Naniat Muglin Road itself. This is one of the problematic section of Naniat Muglin Road, which is at present it is controlled by this slope trimming and rock netting technique. This is one of the problem site of Naniat Muglin Road, where the rock mass is sliding from its joints. For the slope stabilization works in such type of roads, we have found that the following engineering studies are required. So the first one is detailed topographical survey with 1 meter contour intervals in a scale of 1:500. Monitoring of movement of all anchor blocks during the study periods. Engineering geological mapping for in 1:1000 scale. MASW, MAM and SRT survey works. Slope stability analysis using appropriate software. And the solution and studies are the includes rock bolts, rock nets, toe wall, drainage, soil nailing and bioengineering measures. Usual survey works such as topographic survey, drone survey, engineering geological mapping, etc. will be required at such sites. So here I am presenting the bioengineering solutions. So many number of bioengineering techniques are here, starting from 1 to 7. The first one is trimming of slopes and overhanging area should be done as necessary. In some cases, the backfill slopes are needed to be trimmed at 15 to 20 degrees. At the present slope, it is steep and unstable. Second one is water flow system should be carefully considered from the slopes, both for seepage water and surface runoff. Third one is the facings in existing reels and shallow gullies are necessarily required, with some live check dams in between. Fourth one is brush layers should be in diagonal in about 10 degrees slope towards the natural gullies, reels, facings. Fifth one, the stone or boulder riprap in deep gullies are generally required, including live check dams where necessary to break the water velocity. In check dams, the middle portion should be lower than the sides so that water will not erode the sides of the check dam. Sixth one, the plantation of local grass such as sito, kaas, salimo, khar, simali, khar in between the brush layers in diagonal pattern as brush layers over jute netting is recommended. Seventh one is live cutting and plants used are to be from local areas so that the survival rate will be high. Bioengineering solutions. The eighth one is jute netting may be required with use of live cutting pegs in steep areas with loose soil materials. Grass seed spreading is recommended in areas over jute netting or open rocky areas. 10th one is the plantation of only shrub trees in HS hillside slope is recommended. Mango and other big tree plants needs to be removed to valley side slopes if planted already in hillside slopes. 11th one, use of bamboo crib walls in slopes where necessary to retain some materials. Earth is recommended. Bamboo crib walls are recommended in layers, especially in the valley side slope where disposal are made. Use of wattle fence in upper part of the disposal or valley side slopes where materials are loose are recommended. Use of dry walls riprap with live cutting pegs where small slopes are to be retained or supported are recommended. use of subsurface drains in various slopes where there are high seepage water. These are the bioengineering techniques that we have used in Naringat Mooning Road slope stabilization works. Here I have shown typical section of study and suggestions. The problem identified at this section was in fault gauge black clay with graphite is seen over here, and suggested measures for slope protection was scarify loose materials, construct RCC retaining wall, provide wire mesh and rock bolts with proper weep holes. The slope stabilization measure is already done at this section. Rock netting and bioengineering works at Kalikola section. I have shown one of the rock netting works we have performed. This is Kalikola section. The earlier, while we completed our rock netting works, it looks like this first picture. And after a few months, say 3-4 months, the same section was looking like this one. Here I have shown the rock netting works in progress by the workers on the hillside. And this second picture shows the scaffolding works that is necessary while constructing the rock netting works. This figure also shows the slope trimming works on the steep hills of Naringat Mooning Road. Both of these figures show the same thing. Here the workers are in the vulnerability of this getting accident, so they have been provided with the safety ropes. Here in this section, this plumb concrete wall is provided along with the rock netting above the wall here. We cannot see it clearly, but the rock netting is also provided above the plumb concrete wall. Here also this bioengineering and rock netting combined approach is done on these two sections. This is the kilometer 27 plus 400, where we have provided the bioengineering works with this water, this collecting channels on the herringbone pattern from the two small this streams, and the same site has been converted to green, and now it is even covered with the bushes. If we visit this site, we cannot identify this failure site. The site is already stabilized. This is one of the jute netting works with live pegging in the Naringat Mooning Road, and the other one is this retaining wall with this bioengineering bushes. This is the completed road section with structural and bioengineering works after 1 year. This also is the completed road section with structural and bioengineering works. From this, we can draw a conclusion that the specialized work of rock netting with bioengineering has been successful, and no further slope failures and road closures took place in these specific sites after interventions just before the monsoon of 2018. Thank you.
Thank you, sir. That was indeed a very informative, database and visualized presentation on Naringat Mooning Road. Now I would like to ask my co-MC partner to take on the podium for remaining part of the program. Thank you.
Thank you, ma'am. It has been a really great program to this session, and I'll wish to continue this tempo till the remaining session. And without any delay, it's now time for us to move on to our next keynote speaker, Dr. Mohan Prasad Acharya, Geotechnical Engineer, NEA Engineering Company, for his presentation on natural and chord slope stability analysis and monitoring. May I request every one of you to welcome him with round of applause. Thank you.
So, good afternoon, everybody. Actually, at the first, I want to return one word, the keynote speaker. Actually, I don't have done that much, and just my presentation, I will say, is a collection of different stuffs. So many of you must know the one food in the Western recipe, the stuffing. So they put together different things, and at the end, sometimes the taste is good, and sometimes maybe not. So hopefully you'll enjoy it. So I'll go with the topography of Nepal, and the main features are our Himalayas are characterized with rapidly changing topography, and so consequently numerous slope hazards in different engineering structures, and maintaining stable slopes and providing necessary access in road and other structure is very challenging. And our natural slope is more than 70% of the natural slope is between 30 and 60 degree, and our rock wall extends several kilometers up and down, right? So in this context, I think it should not be the special seminar. It should be a normal seminar for us. Okay. Outlines, I try to cover some typical soil slopes and rock slope failures in different parts of the world, and natural slope and cut slope, same thing, and a slope monitoring system, not typical modern, but in contemporary after 2000, and some slope protection measures, general, and I tried to cover very little on the stability analysis and the failure prediction. These are, I think, the new things. Our MSc student might work on this. Okay. The natural rock slope hazards, as my previous presenter already presented, encountered in road and reservoirs, for dams, and river valleys. And similarly, cut slope or built-up slope hazards we encounter in open pit mine slopes. That's not that doesn't exist in Nepal yet, but maybe in recent future, after 10 years or 15 years, it will come. And other one is slope failure during the deep dam foundation excavations. We are designing several mega size hydropower projects with 100 and 200 meter high dams, and sometimes the depth of bedrock is at 100 meter below the riverbed. In that condition, we have to excavate all the way down to the 100 meter, so we'll have the rock slope stability problem in there. And the next one is for surface powerhouse excavation. We already faced it in several projects, and still some are coming. And next, we don't have it because we only have one embankment dam in Nepal. That's Kolekhani. That's 112 meter high dam, rockfill dam, and it not failed. So we haven't done nothing, but it may come in the future. And next is the rail or road embankment failures. One of the evidence for this one is CP Railway, that's Canadian Pacific, because I came from there, so some example of here I use are from Western Canada. It was almost 7 kilometer long embankment, up to 20 meter high, and relatively on the weak foundation, and it fell before they operate the train. So there is a possibility, because we are going to build that train in Therai soon. So when I start with some natural slope failures, this is the Arun River in eastern Nepal, near the Chinese border. So if you see here, you can see the biggest curve, and this is the river is flowing in that direction. This is the right bank, and this is the left bank. So this is the failure that's this generation of people felt it, and it was 70 years back, and all the mass started to move from here, this point, around 3200 meter elevation, and it went all the way down to the Arun River at 1800 meter elevation, and then made a big heap of the material uneven at the left bank. And same thing was happened here, but we don't know the date. And at that time, 11 people died, and lots of losses of the animals. The dam started to flow after 3 days, but the dam remained up to almost 20 years. After a small landslide, again blocked the river, and then when it broke, and then it washed the dam after 20 years. So, and this is the photograph that we can see here as the small terrace on the left bank of the Arun River. Similarly, it's also in the Arun River. It's the previous one was a mix of rock and soil slope. So the failure started at 3200 meter elevation, and the failure happened in June. That means before the rainfall. So I think that started with the melting of the snow, because that's almost at that place the snow line is around 2700 meters. So it's started up to 500 meter above. So when the snow started to melt, and it disintegrated some part of the rock, and it started at the top, and when it moved down, it bring all the material on top of the rock. And this one is also in the Arun River. It's exactly in the bend. If you see in the Google map, it's in the bend of the Upper Arun hydropower project, one of the big hydropower projects. And it started not from the top, mostly it started from the bottom when the river started to cut the toe of the toe rock wall, and there are some feasible joints, and when it breaks the bottom part in tension, then all the material comes through on that feasible joint set. And this is the next one, is Jure site. You all know more than me, so I'm not going to describe it. And I'll go to some, these are exactly fell slope. So there are also other slopes which are defined as slow moving slopes. And this one is the left bank of one of the biggest reservoir, that's Revelstoke Dam. It's also in BC, Canada. That's 165 meter high concrete dam, and it generates 2400 megawatt. So it's a big one. And this slide is just recently found that it's moving, but in a very slow rate. So less than 1 to or maybe 1 to 2 millimeter per year. And they started to monitor it. Another one is I think it's a very well known. Some of you know. It's Frank slide. It happened in 1903. Several, maybe hundreds people died, and people are working inside this hill. Because they were coal miners. So when it happened at 4 a.m. I think early morning, and then all the miners were working inside, and they can come out. Some of them are trapped, some of them are rescued several days after. And another big slide, it's also for the reservoir. That's you can see at the bottom here, it's a mica dam that's around 200 meter plus embankment dam, and just upstream within 1 kilometer on the right bank, they found, just after the construction of the dam, they found 2 big slides. And these slides, this one is almost 9 kilometer long and 1.1 to 2 kilometer thick slide. It's moving around 5 to 7 millimeter per year, and it jumps when the pore pressure is high. And we are building some of the dams, so I think these examples are suitable for us. Another one. So those are the natural slopes, and this one I don't have the picture because this picture was taken in 1978. It's also for the same dam, Revelstoke Dam, and then when they were excavating a 14 meter diameter diversion tunnel, and they had a failure on just upstream of the diversion tunnel. And you can see, I think, just here, the heave of the around 14 million meter cube of rock, just once. And I think there are very less fatality. Next one we have is from Upper Sanjan. It's a back slope of the powerhouse area. Maybe some of us know. It was in 2016, and the failure occurred after they were excavating the back slope for the powerhouse. And it suddenly collapsed in the morning, and luckily there was no casualty as well. And next one we all know is the slope of the descender of the Kaligandaki River. And there are some other examples in the failure in the embankment. This is also from the Thompson River Valley. It's in the northwestern BC. You can see the tracks, the railway tracks going here. One is on the upper part, and other one was just on the bottom part. So there are two tracks, and the whole slope collapsed to the bottom tracks. And the last one, I have an example from our very big project, Fast Track. And this is, you can see there are no things. So can you guess what might be the triggering factor here? So it's the toe cutting from the river. So when they were building the road here, and the river swelled in like 100 years flood, and then it eroded the bottom part of the rock wall, rock and collobium wall. It's not continuously rock, but some part is collobium and some part is rock, and it just caught the bottom, and it triggered the rigs on the top of the road, so it has to be again protected. Another major, I think, cut slope stability issue that comes in the open pit mine. I already said we don't have open pit mine yet, but all the slope stability protections, analyses, softwares, and the equipment, they are developed from the open pit mine experience. These are really huge mines. Some of them are like nearly 1.5 kilometer deep. And the operation of open pit mines is really complex things, because the peoples are working there, and you have to protect the people, you have to evacuate things, and you also has to know when the slope is moving, so when it will fail. And that has to be monitored. And this one is one of the mines in US. So other one is the copper mine in South Africa. We don't have that big mine yet, but hopefully if we get some more metals, then we can have mines. Sorry, 2000, I think it's 2002. This one is 2002. I don't know the date of the previous one. Yes, in 2002. Sorry. So I jumped to the slope monitoring. As already said, I just collected things together. So what the instrumentations we use in the monitoring of slopes are inclinometers to measure the deflection, and one new thing, step accelerators. That one I used. It's a three-dimensional array. It comes in 30 centimeter long, 30 centimeter long sensor, and it can measure three-dimensional deformations, X, Y, Z. But it's complex. If the slope is moving really slowly, it's very difficult to determine which direction it's going. But if it is it's moving in single direction, it's very particular, and it's a real-time monitoring. That means you'll get the data in real time. Like in the inclinometer, you go and put the instrument only. Let's say if you measure today and then tomorrow, then you'll get two data, right? But in the case of step accelerator, you can get the data every 10 minutes, every 5 minutes. You can customize the data. Next one is the piezometers that I think we are all familiar with. Piezometers can be piezometer. I have a detailed photograph as well. And next method is LiDAR scanning. It's just like a scanning of the surface today and tomorrow, and they get the difference. The other one is the ground-based radar scanning. It also monitors the slope continuously. We put the radar here, and then show the direction of the slides, and it gets the difference in the distance. I'll show the picture. Another one is we haven't used, but it's in the developed country. They use the satellite monitoring with ground-based reflector at different points. Here is the shell of the inclinometer. So we put it's with from the group. We insert these measuring instruments, and then we get the point, the position of the inclinometer at that particular time. For the shape axle arrays, these are the arrays. They come in 7 meter, 9 meter, and I think even longer if we want, but they are pretty expensive for us. It's like it was $150 per feet. So pretty expensive, but how we can use it? It's on a slide. We can put this arrays like vertically, and then if it is moving in this direction, then you'll get the real-time data. Also here it's showing the concrete putting of the bridge, and you can put together, and it can be placed just in the tunnel like an extensometer just around the tunnel. Next one is that ground-based radar. It's we put this one in front of this Frank slide. It was in 2010, and when we were putting there, it was -39, the outside temperature. And this one is really heavy. It's more than 250 kilograms, and it needs a crane to lift the things from the ground to the top of this small hut. But how it works is you can see the two lasers here, laser source. So it continuously emit the laser to the slope, and then when it return back, it just record the difference time. So let's say if the slope is moved 5 centimeter, then there should be less time for the laser to travel from the source to the slope. That's how it works. Next, we know the piezometers, but piezometers can record there are different type of piezometers. Some record the static data and some can even record the dynamic data. Let's say when the train pass or when there is an earthquake, and they can automatically trigger to record the pore pressure. They can be programmed like that. And the most effective things in the pore pressure measurement is, let's say, in the soil slope, when we already know the slope, the shear plane. Then what can we notice in the pore pressure is if there is a shearing or is there acceleration in the movement, we can feel the acceleration in the pore pressure generation. That's how we'll get the information in the piezometers. Okay, so not detailed, but I just summarized some of the slope protection measures. I haven't gone to the stability analysis yet because that's a really big thing and it takes time. So what I suppose, the slope protection measures are based on following factors. The first thing, we can achieve the slope stability from the reduction of the pore pressure, most of the cases, if the slope is not drained and full of water. And the next is the reduction of the slope itself. That means change in the slope geometry. And third one is we can protect the slope bottom from erosion, slope itself, slope surface from erosion. That's how we do, I think, in bioengineering. And the protection from toe cutting, that we put the toe wall. That's why if there is the support at the toe, then it will not move on the top. And next one is slope reinforcement. What I mean with this is either the bioengineering reinforcement or the short bolts that we don't anchor, we just put it there, like in the rock bolting in the tunnel. And next is the slope anchoring. Like if we have a big block, and then we cannot just put the bolt In that case, we have to tie that big block in the like a stable rock surface. That's slope anchoring. And another one I will say is the same thing, but it works with the slope anchoring, but we break the kinematic feasibility of the whole rock structure, like the joint and the foliation planes structure. We add something and then we break the feasibility. And another is breaking the moment along the shear plane, that we can introduce, let's say, toe support, or even increase the load at the toe. There are different things. So I have some examples. And this one is again the example of the Dutchman Ridge. That's just upstream of the Mica Dam I just described. And this one includes almost 9-kilometer long drainage galleries with at different directions. And then they measure, you can see here the pore pressure before and after the introduction of the drainage gallery. And this pore pressure reduction will certainly increase the friction parameter, I suppose. And that will help the reduction in the rate of the slope movement. Next one is again I'll come to the back slope of the upper Sanjin powerhouse. In their powerhouse, we tried to change the geometry by removing the top unconsolidated soil mass. At the beginning we tried with a bottom toe wall, but at the end when we excavated from the top to bottom and used the reinforcement, the surface reinforcement, it worked, and then there is no need of the bottom toe support. Next one is I just talked about this big rock mass failure at the intake of the Revelstoke Dam, and they introduced here, you can see the two big anchors. They anchored these whole blocks to the stable rock mass, and plus they use these piezometers to continuously monitor the movement. Another one is, we all know the right bank, left bank of the Kaligandaki River, the descendant area. There are numerous anchors and the rock walls established, and you can even see the piezometers. But I don't think anybody has checked how the anchors and piezometers are working or not. But it's still the slope is okay. So. So I will come with this one. So this has one particular thing. This again the slope of the Dutchman Ridge. So there was a big question, why it's moving on 6 to 7 millimeter per year but didn't fail. And the most of the people's analysis was because of this toe weight. So if we remove this one and just analyze the slope, then we'll get the factor of safety less than 1. So it is in the road excavation and in the river valley like construction and the dam excavation, it has a big meaning in the consequence. What is the consequence? We don't care. We just cop at the bottom and see the upper slope. And next is it's again the toe at the corner of the upper Arun project, where the Arun River bend. You can see this one, like it's not the foliation, but it's one joint, and it's just like provide the kinematic feasibility of the whole upper part of the failure. So the bottom part is started not with this, just with the tension fail. At the bottom the rock failed in tension, and when it come to this joint, and it just couldn't support the upper part, and it just moved at, I think, at one point. And next one I will come. This figure is you can guess. The Bagmati River is cutting the toe of the whole slope, and this threaten the upper slope of the recently cut sections. And I don't have any details. Okay, so I'll come to the very briefly into stability analysis, because I think it's a really big and important topic, and like I could not cover just now. But for the slope stability analysis, what I suppose is the slope stability methods, the important factors are first formulation of the failure mechanics. And what we do next is we use the commercial software, but what we use the same commercial software and for the swell slope and for the rock slope. And for the case of I just showed the road section, it has the rock outcrop every 10 meters. And in the middle, there is a colluvium. So where is the failure plane? We put the uniform homogeneous material all the way down and use the software. So you can judge it. You are ours, geotechnical engineers. And for the soil slope, I think if the dominancy is the fine grained soil, most of the slopes are pore pressure driven. So we can manage the drainage efficiently. We can hold them, and we can still use the HM as the homogeneous material, and also the slope geometry and slope material as well. And next thing is I'll just briefly want to say factor of safety. What is the factor of safety? I think it has the variable meaning. So it's just one means if it is in the existing stable condition, one means the stable condition. But when we analyze and we get, let's say, 1.5, what does that mean? It should be the knowledge-based factor. So how much we know the mechanism and how much we know the material parameters. It should be guided on that. If we don't have the good knowledge on the mechanism and the material parameter, we should have the higher factor of safety. But we know exactly what is that. Then we can even, I think, provide 0.9. Some of our slopes stand even 0.7, right? And next, I will say some of the steps for the modeling of slopes and protection, and hopefully it will work. The first thing is the determination of the slope geometry. We all know that. And then second, and the most important, I'll say, is the identification of the failure mechanism. How the slope is working, how the slope is moving, at what plane, if it is the homogeneous material or the non-homogeneous material, if there is a predefined failure plane or no predefined failure plane, we have to do that. And third is the stress state, including the pore pressure. But we mostly, we have no measurement on the pore pressure, right, in our slopes, so we just assume the line. And third, the fourth will come the selection of the material parameters and the material model. Once you know the top three, then I think that's a straightforward. And next, more important is the introduction of the protection work. And the last one, it should go and back and forth with the introduction of the protection work. We have to check the stability analysis with and without protection work, and that should include the structural as well I think I'll say the hydraulic stability. If it is in the valley. And next one, as I already said, the prediction of slope failure. There are lots of work done actually in the open pit mine field. Some people, there are lots of paper, you'll get it, how to predict the failure date. So if you can predict, okay, this slope will fail in the March 3rd, then you will get lots of money. Who will try? Who wanna try it? I think our new engineers. Thank you.
May our fragile slopes be well equipped with inclinometers and piezometers. May no Jure landslide repeat again. And may your work turn out to be milestone for coming future. Now, ladies and gentlemen, we have come to the time for the last but not the least keynote speaker, and shortly we are having a question and answer round at the last. Ladies and gentlemen, we have come to the time for the last but not the least keynote speaker of this seminar, Mr. Dennis Gross, MSc Geology, Regional Manager Asia Pacific North. He is also representative from GeoBrock, Switzerland, today's sponsor, and his presentation is entitled Slope Protection System. I request every one of you to welcome him with a round of applause.
So, ladies and gentlemen, Very warm welcome also from my side. I'm Dennis Gross. I work for a Swiss-based company called GeoBrook. And I like to thank NGS a lot, also Uttam and Suman, helping to make this event happen. And today I try to contribute some points on how GeoBrook or how we do slope protection, rockfall protection works in other parts of the world. Like to contribute because a lot of the things which I will mention have been mentioned before already. But this is of course because we are here geotechnical experts, so we talk about the same issues. So there will be two presentations actually. The first one, this one, will be dealing with slope protection, and the second one will focus a little bit more on rockfall barriers and debris flow barriers. So this is the agenda. You can see I will give a brief overview and background of where I'm coming from. I will raise some questions on stability problems, on the stability analysis. Then we will talk a little bit about hard, flexible and soft facings to cover the slope. Then I will introduce the system which we promote, the application we promote. I will lose some words on the Ruvolum concept, which is the dimensioning concept, which is behind our application. Show you a short case study and a couple of references worldwide. I put a lot of pictures. The company GeoBrook actually was part of a company founded in 1836, where they produced hemp ropes for the sailing ships. And then after the use of sailing ships declined, this company started to produce steel wire ropes to actually, well, what we still do today for cable cars or for structural bridges. And then by the mid-20th century, they started to invent or produce these very simple avalanche protection systems with two wooden posts and put a steel wire rope net in between to hold the snow. And during summertime, they recognized, okay, there are rocks in those nets. And that's where GeoBrook started to think of in the middle of the 20th century, okay, we have to develop those systems to actually create flexible rockfall barriers. But this will be then the second part for my presentations. The other thing is the material which we use is unique. We use a high tensile steel wire, and this enables us, which you will see now in the later slides, to do certain things. And for that, actually, I want to draw the attention of you. In the seminar package, you find this little flyer, and inside you have two different kinds of wires. And I ask you to do now or to do later at home or in your office with your friends, try to bend those wires. You will find one of those wires can easily be bent by hand, without tools of course, which is a mild steel wire used for gabions, for example. And the other one is the high tensile steel wire. So this is almost all what I will tell you about promoting my product actually. We can see here the different kind of applications we can provide to mitigate geohazards. We will focus here on rock slope and soil slopes, and then in the second presentation on rockfall barriers. You might recall this sketch, a similar one from Shankar's presentation, and we'll have a look there at the debris flow mitigation. So stability problems. While I was preparing this presentation, I found this graph from Dave Pedley, who is a professor in England and the UK, but he's also doing quite a lot of work worldwide and especially also in Nepal. And you can see here the spread of fatal landslides in the last maybe 10 years. And this blue line here, this is actually South Asia. and these lines here are Southeast Asia. So this is an issue. I think this is something we have to ask ourselves. Why is that though? Is this only because of climate change? Of course, earthquake, like the Gorka earthquake, has an important impact on those landslides. What can be other reasons? Informal road construction, for example, or simply the geological complexity that has been there before, ever since. So if we look at the general problem which we deal with, I'm not going into the detail here because this is a very simple sketch which we know all, but the main triggering effects, of course, are gravity and water. And I appreciate very much that also in the former presentations, almost each of you have been mentioning take care of the water. Whatever design you do, if we forget about the water or underestimate the influence of water, this will create a problem, at least a problem, if not a failure. So a couple of slides to just illustrate more or less simple stability problems. This is from a project in Germany, slope failure due to water saturation. Then we have these type of failures on convex slopes, of course. And other problems, for example, can be that the stratification is unfavorably orientated. We cannot see here directly, but these sandstone beds, they dip all towards the road. So stability analysis. Before dimensioning, we are urged we need to do a proper site investigation. And if we don't have proper data, then we can discuss the factor of safety. So information needed from the site must be sufficiently understood. We need to know about the geometry now or also after we cut the slope. We need to know about the water conditions. And the geology, of course, has to be sufficiently understood. So this is also, we go quickly through that. There are a lot of different issues, that was too quick, which we have to deal with. Since, we are geotechnical experts, this slide is rather boring. So if we look at slope stabilization, I would say from our experience that we either deal with superficial instabilities, so a kind of superficial erosion or a superficial sliding plane, not too deep, which is actually the bigger part of the projects, or we deal with deeper seated sliding surfaces. If we deal only with superficial instabilities, then, for example, our Ruvulum concept or the design software is capable to provide a design concept, give you a nail pattern, nail distance, nail length. Whereas in cases where we have deeper seated sliding surfaces, we will have to analyze the global stability first. There are various commercial available programs to do that. They have different theoretical models behind it. We mostly use a Bishop circle, but there are other circle types and models which you can also easily use. So for deeper seated sliding surfaces, first we would do a global stability analysis and then investigation of what happens between the nails. And for superficial instabilities, we would go with an analysis of the slope with this Ruvulum software. This is just a different force transmission. This is an issue we face, or I face very often, that there is, even in the geotechnical society, not of Nepal I would say, but in general, globally, there is sometimes a little bit of confusion about what we are talking about. On the left-hand side here you can see this is an anchor, which is a real anchor. It's a pre-stressed anchor. That means we only mortar the bottom of the anchor, of the rebar, of the strands. And this, of course, then has to lie behind the sliding surface, which you can see here. Also, then we have the free anchor lengths, and you can see here also that there is a very high load of force at the head of the nail then. That's why, for example, we do those pillows at the nail of at the head of the nail. Whereas in most applications, when it's about the slope protection systems I'm talking about, we will use nails which are fully grouted and will transmit the force, the load, through the skin friction. And here, the load at the head of the nail is smaller. Sorry, it is smaller than in an anchor case. So this is something I find very often. I find there's a little bit of confusion. Are we talking about anchors? Are we talking about nailing? Then if we talk about the foundation of rockfall barriers, yeah, we anchor them, but in fact they are micropiles. So this is something to keep in mind, I think. So when we talk about the facings, we can diversify into basically 3 different kinds of facings. We have hard facings, mainly dealing with any kind of concrete structure. We have those soft facings, which are generally, for example, geosynthetics. And we say we have those flexible facings, which are all sort of different kind of meshes. So with the hard facings, shotcrete is one of a very widely applied method all over the world. The problem with the shotcrete is, from my perspective, very often that we cannot see or we cannot control what the water is doing behind the facing. And even if we put the drainage pipes according to the design, have you ever been trying to do maintenance on those drainages after 5 or 6, 10 years? So depending on the fine-grained material behind the facing, this is going to be a difficult issue. So here you can see also one of a typical shotcrete failure. Other hard facings, for example, are those concrete grid beam solutions, widely used in Japan. You can find them in Taiwan, for example, or in other countries all over Asia and also South America. Problem what I see with them is, for me, they are extremely time consuming. To build all those formworks and then reinforce it properly, that's extremely time consuming and costly. And another disadvantage from my point of view is just that it's a brittle structure, and especially in earthquake prone areas, they are very vulnerable. So I have one, I would almost say nice example, but I don't like the expression nice because it's dealing with this Fukushima earthquake. Both those projects are in the Fukushima prefecture, and you could see here on the left-hand side, you can see the failure of this concrete grid beam structure, and here on the right-hand side, you can see you can see both devastation and also this techo slope, stabilized slope with high tensile steel wire mesh, which is still intact. Soft facings, geosynthetics in general, very good for erosion control, for slope stabilization, rather not. And then when we come to the flexible facings, there are a couple of older systems, and also this picture here, or the pictures you can see here, is from a system which has been introduced by Geobrook in the 80s, which uses mainly wire ropes. The main problem with the wire ropes is that, again, it's very time consuming to install, and you are pretty much bound where you put your anchors, because the nail pattern has to comfort the mesh panel size you use, which is from a geotechnical perspective a big disadvantage, because I want to put the nail where I think it's necessary. I want to put the nail in intersections or under overhangs actually. So when we talk about high tensile steel wire meshes made from GeoBrook, this is a mesh family which we call TECO. It's basically consisting of 3 components. It's these steel wire meshes with different openings and different diameter of the single wire. You can find a couple of samples when you leave the room on the left-hand side on the table. There are different kind of bearing or spike plates, how we call them, which sit on top of the nail. And there are these connection clips, also made from high tensile steel wire to connect the mesh panels. Like that, we are able to create a homogeneous area of material with the same strengths, and we can place the nails according our geotechnical requirements everywhere in the area. Additionally, of course, we need nails. Here also, we have the usual rebars. Let's call it rebar. It's effectively a rebar. But especially in the soil conditions, self-drilling nails or so-called hollow bars are recommended, because it makes it much more easy to drill and grout the hole in the same time, rather than to fight with collapsing holes before you can insert the rebar or the grout pump. So as a summary, for this TECO system, there's a static function, which you will only learn in the slides afterwards, using high tensile steel wire meshes. We have a very high bearing capacity with those meshes, of course. It can be pre-tensioned against the slope, and it can be dimensioned. So this will be the next part. I will talk a little bit about this RuVolum concept. This is the name we have given the baby, this software or this dimensioning concept, which is an online software. So if you are interested, you can register on the GeoBrook homepage. There are no costs or anything involved, and try to work with the software. So basically, RuVolum investigates the superficial instabilities, and it will basically investigate those 2 cases, which you can see here. One is the investigation of the local instabilities between the single nails, and the other one here on the right-hand side is the investigation of the slope parallel superficial instability of this unstable layer here, the yellow one. These are the sandbox tests we have been doing, or not the tests, but the sandbox studies we have been doing in 2000, actually to learn more about the deformation and at which places which deformation takes place. In 2015, we have been doing that in a one-to-one situation with this large sandbox. So this is filled with material. There's a mesh on top, there's some nails. We do laser scanning to measure the deformation. There are strain gauges in the nails to measure the load there. And I will show you 2 or 3 more slides of the results after this part. So this is going back to the investigation of the instability between the nails. You can see here, this is a limited equilibrium equation, investigating the stabilizing force which we need to stabilize the materials here in between. We will take into account the cohesion, the volume weight of the material, of course. And I want to draw your attention shortly at this side where we look at the slope. So the red points, the red dots are the nail heads. Because if we look at this cross section, we will apply pre-tensioning force on the head of the nail, on the spike plate, of 30 to 50 kilonewton. And this pre-tensioning force actually will neutralize part of the weight of the dead body between those nails, which enables us to widen the nail pattern. We don't have to stick to a 1.5 or 1.8 meter distance nail pattern, because we will stabilize some of this weight already with the active pre-tensioning. So then we have, at the end, we have here then two decisive mechanisms or forces. One is the proof of the mesh against the shearing off here. And this is why it's so important that we use a high tensile steel wire mesh. And so we don't have experience of puncturing here. And then, on the other hand, we have this force Z, which is the proof of the mesh for the selective transmission of the force. The second investigation, of course, relating to the slope parallel superficial instability, I think we already see that the decisive point, if the unstable layer is getting big enough, the decisive point will only be here the shearing of the nail, also the diameter of the nail. Also, in that dimensioning concept and in the software, you can introduce a load case of earthquake simply by increasing the weight of this dead body with the acceleration factors of the earthquake or of the assumed earthquake. The same, of course, then can be done with streaming pressure with water influence in the slope. I have a quick case study of a project in Colombia in a place called Cali. We can see here a residential building built in 1995. You can see the slope here behind. And very soon after the people moved in, they started to have issues with that slope. So that was in 2007. And then in 2008, the retaining wall in the backyard gave way. And then in 2009, one of the residentials, of the remaining residentials, because a lot of people moved out already, he took this video from his balcony of the ongoing collapse of the slope behind them. And this is only after that event that the client actually, the client and the consultant approached us to develop a proper solution. So this is again a very nice example of geotechnical know-how, or geotechnical engineers get very often only involved into the project when a failure already happened. It's not very often that they have a video of the failure of the slope, which we can treat then afterwards. We have been done trimming of the slope, of course, first. Then also here they drill with the use of scaffoldings. At the instruction on the site this was the first project ever in Colombia, so we had to send people to instruct the contractor how to do it properly. And this is then how it looked in 2011. People moved back in, all fine so far. A couple of pictures of a couple of projects all around the Asian region, where you can see different applications on roads, like here in the Philippines. This is a limestone a project in a limestone cliff, or limestone geology. This is the very same, just pictures from a drone. Then here we have a project where you can see there is a kind of bedrock, but we also had to retain the colluvium lying on top. This is the very same project. All those projects, especially in areas where there's a lot of rain, we will recommend or advise to use hydroseeding afterwards, so we have a quick revegetation of the slope, which on the one hand side, of course, will make it look nicer. On the other side, it will enable us to have a certain control of the surface water also. And of course, the small roots will also contribute to the stabilization of the first 10-15 centimeters of the slope. Another project here during excavation. Not always are the conditions like that it's so easy actually to install it. You can also see that the drilling machines they use here are lightweight drilling rigs, which are very easy to move over the slope, so this will also save time during installation. One more project from the Philippines. Since the Philippines is within my responsibilities, a lot of pictures are from the Philippines, I'm sorry. We have this big project we have been doing in Mindanao on the Philippines with this superficial erosion here of these very weathered andesite materials. This is the very same site and just after completion. Then I can also show you some pictures of a project in Vietnam. So this is a relatively small site. The height is maybe like 15 to 18 meters only in a rock environment. And we have this rather high slope where there was initially a shotcrete installation, which you can still see here at the side, which failed. And then we covered the whole slope, including the shotcrete, with one of the high tensile steel wire meshes. It's just another perspective. Small project which we have been executing in Indonesia, like but almost 90% steep in a very different geology. So this is a volcanic deposit which is called lahar, which especially in connection with water can be very unstable. And a couple of examples which had been executed just here in the neighboring India. One of Kiratpur-Nachok Expressway. Also those pictures derived from the same project. And one project which is still ongoing on Mumbai-Pune Expressway, where they use not only small mobile drilling rigs, but also drill from those platforms which are hanging on the cranes. So I come to the end of this presentation, and then I have a short video as a summary. So this is the online software which you can see here. This is one project in an abandoned mine in Brazil. That one is in Germany. Here you can also see the effect of hydroseeding. Thank you very much. So in the second part, I hope you are still not too sleepy. it's almost 6 o'clock. We will deal with rockfall barriers and debris flow barriers. So Shankar already mentioned or introduced rockfall barriers. This very picture here is in Nepal. So this is the first Jubrook rockfall barrier project which we have been doing in Trisuli. So in this first part, we will shortly talk about the rockfall phenomenon. I will give a brief introduction about how rockfall barriers look like. I will show you a case study here and a couple of examples, and then we will do exactly the same for debris flow barriers. So the rockfall phenomenon, I mean, this we are very familiar with. And also, if you look here on the right side, at a certain extent, we have to realign the road and we have to resettle people because it just doesn't make sense anymore to deal with certain quantities. When it comes to rockfall mitigation, we need to have something to protect, in this case a road, but it can be a powerhouse or any kind of infrastructure. What we need to determine, and this is very vital, we need to find a trajectory, or at least we have to define a couple of trajectories where we expect that rockfall will happen. Also, very decisive is the size of the boulder, but not only the size, but also the geometry, because boulders of different geometry will behave differently in the rockfall simulation and also in the field. So you can see here we have to select or define certain geometries. You can see here on the left hand side this is a 2D rockfall simulation, and you can see here in the middle part this is a 3D rockfall simulation. So we also need to know not only the trajectory and have a cross section, we also should have data on what is the subsoil conditions over this trajectory, because the boulder will behave very differently if it hits a bedrock or if he hits a colluvium sitting somewhere there in between, or whether he hits, for example, a couple of trees. I had to include those because I was also twice, I think at least twice, I was visiting Sidababa, where we did these 3D rockfall simulations actually. So we have been able to find a company by the help of Uttam and Deepak to produce 3D models with drones. Then we have been implementing the 3D models, and we did various RAMS rockfall simulations. And at one point we abandoned the project because we have been investing already a lot of time. And then we learned DOR is looking into the tunnel solution. Okay. Tunnel is also geotechnical engineering. Yeah, but rockfall simulations, we will receive data such as energy over at all the places of the trajectory, so we can sometimes even decide, okay, it doesn't make sense to put the rockfall barrier here. We have an easy accessible area here, we can put it here, and those rocks from this cliff, they won't reach the lower ground. Also, we will receive data as the bouncing height of the rocks, which is very decisive, because if we install a rockfall barrier which is 3 meters high and the bouncing height is 5 to 6 meters, doesn't help a lot, except that we waste a lot of money there. All this data can also be used, of course, to do rockfall risk assessment, risk management. Here, I actually want to draw your attention to charts like this. So the chart here on the right-hand side, it's from the Austrian Service for Torrent and Avalanche Control. It's an Excel sheet, provides a very, very effective, but of course basic means to define different zones of risk which is data which might help the client to decide, okay, this is the most prone area where we have to budget money first. We don't have money to do everything. So, but then we can tell them, or with the help of those risk assessments, risk management, we can help them and tell them, okay, these are the most prone areas. You need to budget money here first. And in this area, yes, there is a certain risk, but not as much as compared to the other sections. So you can allocate money maybe in 3 years. Also, this is one of the slides where I have to point out again why it's so important also in rockfall barriers that high tensile steel wire is involved. We have been not only successfully testing, but also now installing rockfall barriers with a kinetic energy capacity of 10,000 kilojoule. So this is a block of 25 tons falling from 42 meters height. And that means that this energy, well, the deflection which we have been talking about, or Shankar has been also mentioning, will be in this case for this barrier 8 meters. And it means also that within 0.5 seconds, the mesh or the barrier actually has to dissipate energy of 290 tons. And this is why high tensile steel wire meshes are important. Okay, short resume, stabilization versus protection. On the one hand side is what we call active protection with soil nailing plus meshes. No maintenance required afterwards. What you have to keep in mind that it takes longer, of course, for installation time, and if you have huge areas, it's not economical anymore. Then you could move to protection through rockfall barriers, because there you only have to install a single line, which is done quickly and which will cover or can cover a bigger area. I'm very happy that actually I can skip this because Shankar also showed this slide, how rockfall barriers look like. There are posts installed on base plates which have a foundation, which are anchored. There are certain retaining ropes, and in between you find either this big brother of the Teco family or those ring nets made from steel wire, high tensile steel wire to retain the rocks. I skip those because I think I will be running out of time. This is a nice short video which I want to show you about one of the tests in those canopy situations, which Shankar also mentioned earlier, which is self-cleaning in this part. But those barriers, those canopies as we call them, or yeah, it's like a rock shed actually, they only work until a certain energy. So well above 2000 kilojoule, we haven't been able to do it until now. But for the lower energies, they work very well. Of course, you cannot have any infrastructure below the road you want to protect, for example. What is or might also be very important for the client or also for a tender, that those barriers are specified according to certain guidelines. There's a couple of guidelines. One of them is a Swiss guideline, there's a European guideline, there is an Austrian guideline. They differ in certain details, but in general they define a quite good quality level of guide barriers. Also, what we do very often, or we need to do very often, especially when we come to customized projects, that we do those simulations with finite elements. Mostly we use Abacus, for example, one of the other of you might know, to actually see where are the highest loads in the mesh components or in the components of the barriers, which you can see here in the yellow or orange colors. The next one is the next one is showing the influence of different rock shapes. We have here a rockfall. This is a research project with a Swiss research institute. This is a disc shape rock who behaves totally different than, for example, a spheric type of rock would behave. And this is a very important issue where we actually, as GeoBrook, together with research institutions, want to push more. So we have more testing under real nature conditions and not just a test in some abandoned quarry to actually compare different kind of barriers, but to learn more about what happens if a different geometry of boulders hit the mesh or the barrier not only in the center but also in the outer fields, or not only in the center of the center field but also here in the left corner, on the right corner, and this is a very challenging issue. Additionally, the WSL, they take data from these experiments to improve these RAMs, this 3D rockfall simulation program. So we are looking forward to the results in the near future there. Case study on rockfall. I choose a project in India, which is the pilgrimage route to Vaishno Devi temple. So you can see here, this is the pilgrimage way. It's one of, I think it's the second most visited pilgrimage site in India. You can see these simple structures to protect the pilgrims. And the authorities of the shrine actually contacted us back in 2015. And since then, we have been like almost every year, we have been adding some rockfall barriers, because their budget is also allocated over several years. So you can see here, during the installation, two guys here erecting a post. Quite challenging environment, absolutely, to install rockfall barrier at this position. And you can see down here the track and some of the rockfall barriers over it. A couple of rockfall barrier examples. An example from the Philippines. This time it will be only one example from the Philippines, because we mostly do slope stabilization there rather than rockfall protection. There's one example from Grasberg, which is the biggest gold and copper mine, open pit mine in Indonesia. So they have their facilities down here. They have frequent rockfall. Once a rockfall happens, the regulations say stop operation. They lose millions a day. So that's why they are very much after it to have proper protection. And you can see here one of the boulders which has been retained in this barrier. Other projects from Hong Kong, where we have been installing barriers since more than 30 years now. And again, this project, this picture from Nepal. This was done to actually protect the Trisuli 3A. And it's also in the upper part, but I didn't have any nice pictures. At the very top of the slope, we did also some installation of techo meshes, but I lack the good pictures, and it's not very easy to get there. I mean, I don't mind for the 5 hours drive, it's the hike up to the top. So also to conclude this part, actually I haven't done that video and I haven't asked for permission, but this is a short video I was sent from Nepal on that Trisuli 3A project. So I hope there will be nobody coming after me. Yeah, they built a small ropeway also to get materials more easily to the top. And we installed the barrier also by help of the helicopter because it's not that easy to access the site. This is the upper part of the slope with the Teco mesh installation. And this is definitely a site where they have active rockfall. Again, you might remember this graph. So now we are not on the rockfall side, but we're getting to have debris mixed with water. We have been also developing dimensioning software here. The difficult thing about it is that you can either have mud flow like debris flows, or on the other hand, very granular flows. So this is quite a challenge, or was quite a challenge, to find the good, the valid design parameters actually to create the software. Also in Switzerland, we suffer a lot from debris flows. We have a lot loose materials in the Alpine mountains, lots of gravels. We have no monsoon rains, but we have a lot of strong rains too, which then will finally result in debris flows. And of course, the destructive energy of those debris flows is amazing. Whenever you see the results afterwards, it can be really devastating. So some of the protection measures, for example, have been the construction of big earth dams, or those concrete structure with these steel structures to retain the coarse debris, or those sabo or concrete dams, or sometimes also after been executing these risk maps. There has been also cases in Switzerland where we had to do evacuations and resettle people in other areas. Or, for example, also possible is the installation of those flexible debris flow barriers. Again, that was kind of similar to the avalanche barriers, where then back in the 1950s they discovered, okay, they might also retain rocks. We had a rockfall barrier actually in Japan, and in the beginning of the 90s, there was a major debris flow retained by these rockfall barriers. That's when we started to think, okay, we have to develop this further, because it's a totally different dimensioning concept behind the debris flow than behind a rockfall barrier. We have two types. One is the V barriers, the other one is the U barriers, and this just is derived from these geographical terms for different kind of valleys. And so the VX will sit in V-shaped valleys without any posts in between, and the UX barriers will sit in U-shaped valleys, and we will add posts in between. This is a small video, if it works. Didn't want to hear the sound, but there will be a second video afterwards. So here you can see different load cases which we had to take into account, or which you have to take into account when you deal with the debris flows. And you can see this is very unlike a rockfall event where you have one dynamic impact, even though it might be a couple of instant impact. Here we have to either cope with the increasing pressure of the debris, so we have to stop the debris flow. Then we have this filling event in the barrier to retain the materials in the barrier, and then afterwards we might have such called overflowing events when a second or a third surge of the debris flow will go over this barrier installations. So a couple of pictures how they look when they are filled. Here, that one. What is the height here? The height here is 6 meters. So it's a considerable amount of debris which you can actually retain. But of course, this is governed because of the geometry and the inclination of the riverbed behind the barrier, upstream the barrier. Also, this solution we have been testing together with this Swiss research institute, the WSL. Quick case study again. I will take you to Peru, to a place called Chosica. It's not too far from Lima. We have again here a video from 2015 showing the impacts of massive debris flows on the village or on the small town of. Now the debris flow actually starts only. And there's a couple of gullies all leading to this city, so we only have this video. Here it goes. So again, there have been retaining structures here, and I think another one was over there. The authorities had to rethink about their concept, so they wouldn't again install those concrete dams, but we have been able to together with our Colombian partner, Peruvian partner, sorry, to install 22 barriers here actually. But you can see Chosica down here, and there's like 4 or 5 gullies going down to the city of Chosica. And we have another video during the recent event where you can see the filled barriers here, and they still experience water in the streets with some debris, but not to the extent which you will just also see, not to the extent like in the previous video. So you can see the barriers here filled up until the top. And still water here on the street. Huh? Of course, I mean, we don't stop the water. The water has to go somewhere. Our main issue is we have to collect as much debris, as much of the boulders that we can get. So the previously empty barrier now all filled up. Couple of examples again. I believe debris flow barriers, they also might have, or they for sure have a potential here in Nepal. There are a little bit different applications. For example, here we have been protecting, the consultant was afraid of ongoing erosion in the riverbed. So we installed a series of barriers. We will not be cleaned. I'm almost finished. Thank you. Which will not be cleaned, just to protect the riverbed from further erosion. Another example, for example, is this, where this check dam, which you can see here, the foundation was scored, and the consultant was very much afraid of failure of the whole dam. So we installed these barriers to collect debris to protect the foundation again. And one last example here from the Philippines again. And with this last slide, I conclude my presentations. I would like to thank you very much for your attention. And I give over to you.
Thank you, sir. We hope that soon our slopes be equipped with appropriate modern technology. Now, a short information to every of the participants. This is to inform all of you present here that Nepal Geotechnical Society is attempting to make all its activities online, and for this we are soon collaborating with Khalti for online payment and internet management related to Nepal Geotechnical Society. So in coming days, direct payments for program like this can be made through Khalti. So in coming days, we will be having sessions where we can have direct payments through Khalti. Thank you. And moving further, without any delays, with slight delay in our schedule, I'd like to move further in our program. And as per the schedule given in your hand, we have a guest remark, and for that, I'd like to call Engineer Tukalal Adhikari, President of Society of Consulting Architectural and Engineering Firms, for his remarks on today's program. Welcome him with round of applause.
I have the pleasure of concluding this very interesting seminar, half-day seminar, organized by Nepal Geotechnical Society with collaboration and sponsorship of many institutions, many companies and institutions. Well, this event to me seems to be very, very interesting one. Although it was not interactive at all, there were no questions from audience, but I believe most of you must have been refreshed with your knowledge of geotechnical engineering or slope protection methods, and you may be looking for some more information while you will be working in the field of geotechnical engineering, mainly slope stability aspects. Coming to the presentation, because I'm also required to conclude something. So first presentation was from Dr. Shankar Dakal. So it was very interesting one, combined with science of rockfall as well as some practical aspects taken from example of Nepal, Siddha Baba, which is one of the very, very critical rockfall area in Nepal. Many hazards have happened in the past, and Department of Road is interested to solve that problem. So he had good opportunity to work in that one, and he, as team leader, he suggested something very useful. Hope Department of Road will take into consideration of this one and go for implementation or avoid the problem with tunnel or other things. So it may be his solution, rock net, fence, as well as rock cell, rock set, or it may be some other solution to avoid that hazard prone area, to mitigate the hazards. So he nicely combined this science as well as practice in slope rockfall protection, basically. So thank you, Dr. Shankar Dagal. Next presentation was from professional engineer Rohit Bisural from the Department of Roads. Well, we had some opportunity to work together along Naranghat Mugling Road for some time. What he presented here today is mostly based on the experience of mainly it's rock netting works and bioengineering works. Those are applied after 1 year before, and still the stabilization process is continued. There are some more sites. Well, that time 29 sites were treated, and all of them are highly successful, I would say, more than 90% successful. And then this year again, there are 8 hillside slopes and 3 valley side slopes. There also some sort of solution like that is being conceived and designed, and it's being implemented at the moment. I think it's high time for geotechnical engineers as well as road engineers to visit Naranghat Mugling Road at this point of time. You will have opportunity to learn about these innovative type of things. Well, for us, for Nepal, we still say that this rock net and these fencings are innovative ones, though they are very much proven outside. We have just introduced quite recently. I think it's only after Gorkha earthquake of 2015. There were some efforts to introduce this in Nepal. So to take name, well, we had Bhotekosi project where one sort of this rock fencing barrier was introduced, and then Sita Baba where trial demonstration was done, and then Naranghat Mugling Road where at least 12 sites were treated with rock netting. And then I think this very interesting one presented by the last presenter, Danish Grus, that Trisuli 3A, that slope, it's a high slope, very difficult slope, which was, these were introduced quite recently, all within last 2-3 years. So this field, this slope stabilization and this hazard management, this is still evolving in Nepal, and many innovative things are coming up. So we, geotechnical engineers and slope stability management engineers, we need to learn about those things. We must be vigilant about the developments going on around, and we should try to get to those solutions to the best of our purpose. Thank you, Rohit Visural sir. And third presentation was from Mohan Acharyaji. Well, he covered, he presented many different aspects around the world, well, Canada mostly and Nepal, and many slope stability aspects. And then he also describes how slope stability can be improved or mitigated. And of course, he also described how these methods of investigation and analysis, and also presented some interesting case study of this upper Sanjan powerhouse back slope, which was designed as supposed to be good rock slope, slightly trimmed, and powerhouse was to be constructed at the toe of that slope. And then, of course, little bit of shotcrete and small dowels, maybe 1 to 1.5 meter, and that was constructed from top. And there was a plan to make this toe wall at the end, but that solution did not work. Well, there was failure, and after that failure, we had the opportunity to work together and to find out some solution. And finally, we have to trim some more, remove colluvial material, and and this jointed rock. And then we came to some solution that is working nicely. Of course, we had to shift the powerhouse by some distance to the to make room for future events, or to give room for the stability solutions. So that was also very interesting, and he also presented about this hydropower projects, medium or even bigger hydropower projects, which is currently working with any engineering company, and they have taken up, I think, 6 or 8 hydropower projects, which are quite big ones, and that is all from local expertise, and they are facing with all sorts of geotechnical problems. And so I think this team will find good solutions for those hydropower projects, dams, and slope stability. Thank you, Mohan Acharya. And the last presentation was well, even more interesting from the perspective that many innovative things, mainly these rock barriers, it's avalanche protection, it's rock netting, and these things are now researched to a high level. I mean, for our case, we are considering them as very new one, but this company, this Geo Group, Swiss company, they have, I think they started almost maybe almost 100 years ago, and now they are still researching and innovating. So every time after every application, they are innovating with material. There is innovation in material property also, and also in concept, design concepts, in the requirement of this resilient and this flexible solutions. Earlier we had this conventional sort of thing, sabo engineering or rigid check dams or toe walls or those things. But we saw some of the examples we presented that they did not serve the purpose. There are situations where these rigid structures do not solve the purpose. So for that, there's very resilient and very flexible solutions are available. So we need to be aware of that. And it's very interesting that I was also involved a little bit with him. We had brief meeting with him, and we had to find solution for a huge landslide, which he presented in the second part. This Trisuli 3A. This upper part, it's a left bank of Trisuli 3A. This was very, very challenging from topographical and geological perspective, from safety perspective. But this was solved to a reasonable level. Risk was mitigated to a reasonable level by the product of Geo Group. They applied it. It was very, very challenging project, and finally it's working, and safety is enhanced. Well, it's reasonable, and after that, this dam construction is completed, and now that project is already operational. So this very challenging thing was also addressed in Nepal. So we have good experience in Nepal also for this type of thing already. A couple of instances, but we have entered into that, and we have a lot of other areas where this type of solution can be applicable. As geotechnical engineer, if I remember when I studied geotechnical engineering, well, civil engineering, and then later geotechnical engineering, since 1984 and 1998, That time we studied mainly this textbook type of things, shallow failure, do this type of thing, this type of analysis, this type of solution, and then deep-seated, this soil nails, rock anchors, this and that, only that. But within this recent decades, many other solutions have come. So we should not think in the traditional way, that is average, even if it's avalanche, it can be very well treated or mitigated by these solutions. So I think this seminar was wonderful, and we had opportunity to learn much more in that direction, mainly flexible solutions, Rockfall, these solutions. They are not truly geotechnical only. It's a combination, it's a multidisciplinary thing. It's presented by, it's already stated by presenters. It's multidisciplinary. There is a role of geotechnical engineer, there is a role of environmental specialist, there is a role of structural engineer, and almost and many other specialization is also necessary. So with this combination, we can find out some solutions like that that solves the purpose based. So thank you, Dennis Gross. So with this, I think I have done my job. Thank you.
Thank you, sir, for binding up all of the contents presented here in this seminar. Sensing all of the expressions out there, without any delay, I will move forward. Next, as a sincere gratitude to all the dignitaries and keynote speakers who have taken out time from the busy schedule for their very required presence and to share the knowledge and enlighten us for way forward, I, on behalf of organizing committee, would request you to please accept a small token of love and token of appreciation. To do the honor, may I request the chairperson, Dr. Indra Prasad Acharya and Mandip Subedi sir, to hand over the token of appreciation and token of love. And I will read out the names for distribution. Firstly, for token of love, I'd like to request our presenters, first Dr. Shankar Dakal sir, for his presentation on rockfall protection engineering on Siddhababa site. Also, I request Engineer Rohit Kumar Visural sir for his presentation on slope protection works on Narayangarh Muglin Road. May I request Dr. Mohan Prasad Acharya sir for his presentation on natural and cost slope stability analysis and monitoring. Also, I request Mr. Dennis Gross for his presentation on slope protection system and rockfall protection system. I'd like to request our chief guest, Engineer Keshav Kumar Sharma sir, for his token of love. He's absent right now, but also our request on behalf of him. Now I request Engineer Tuklal Adhikari, President of Society of Consulting Architectural and Engineering Firms, for his token of love. Now, we'd like to provide special thanks to all the sponsors for their valuable support in this program, and for token of appreciations to our sponsors. First, I'd like to call Dennis Gross on behalf of GeoBrog for receiving token of appreciation. May I request Engineer Uttamlal Pradhan from East Management and Engineering Service Private Limited for receiving token of appreciations. I request Engineer Uday Neupane sir from Clay Engineering to receive token of appreciation. Thank you, Dr. Indra Prasad Acharya sir and Nandip Subedi sir, and our distinguished dignitaries. Now, without any delays, I'll move further in the program. And again, for token of appreciation, I request Mr. Santosh Thapa sir from Tactical Solutions Private Limited for receiving token of appreciation. Now moving forward, with a slight delay in schedule, we are entering the last part of our program. I request Mr. Shiva Prasad Nepal, Executive Member of Nepal Geotechnical Society, also Joint Secretary of Department of Road, on behalf of Organizing Committee of this seminar for his concluding remarks. Welcome him with round of applause.
Guests of this seminar, participants from different institutions, professors, representative from GeoBrook institutions, my friends, especially friends from Department of Roads and other governmental agencies. Nepal Geotechnical Society has organized this event with some specific objective to provide a forum for discussions among ourselves, among the geotechnical engineers, practicing engineers, professionals, to have common platform to discuss problems, their analytical methods, solutions and implementations, to share some experiences of their own, to share skills of their own. So we have successfully achieved, I think, that objective. When I see Dr. Akal sir present here as senior geotechnical engineer and very young engineers, to bring together themselves in a single platform so that the issues find in many different conditions of slope stability, ground improvement and other implementation issues have been discussed here. It could be discussed among ourselves, though it was not an interactive session today because time was very limited, as Tuklal sir rightly said. But the forum is always open. The Nepal Geotechnical Society has been organizing monthly lecture sessions also in this by this executive committee. We have organized more than 10 lecture sessions. So this is extension of that program. So it is very fruitful, I think. All the geotechnical engineers, practicing engineers are sitting together, having discussions. So it's very fruitful. So in the future also, we are planning to organize such program in future. So I take this opportunity to thank all the participants, institutions, our sponsors, co-sponsors, and co-organizers who supported us to have this seminar successful. And I also like to thank Vivanta Hotel, who provided us this space to organize our seminar. So it's getting late, so I thank you all the participants and request to join in the dinner. And I I inform you that the seminar is concluded. Thank you.